Okay, we're going to do two more examples of error bounds in this video. Here's the first one. So for a particular function, so this time I'm not telling you what the function is, it is known that f of 2 is 8, f prime of 2 is 5, and the absolute value of the second derivative is less than or equal to 3. Approximate f of 2.5, estimate the amount of error. So go give that a try. See if you can figure this one out on your own. Okay, welcome back. Since we only know the first derivative exactly, the exact first derivative, we're going to write a first order polynomial. So f of x will approximately be this first order polynomial, which is f of a, so that's 8, plus f prime of 2, which is 5 over 1 factorial times x minus 2, we're centering around 2 because this was f of 2, to the first power. So simplifying this a little bit, we get 8 plus 5 times x minus 2. And I'm going to leave it like that. I'm not going to distribute the 5 because I know that I'm going to plug 2.5 in to approximate, and I'd much rather it be in this form. So f of 2.5 then is found by plugging 2.5 into this first order polynomial. So it's 8 plus 5 times 2.5 minus 2. 2.5 minus 2 is 1/2. So I have 5 halves plus 8 is 21 halves. So f of 2.5 is approximately 21 over 2. Okay, now we're going to estimate the error, and that's where this last part comes in, because we know that the second derivative is less than or equal to 3. So that's going to help us a little bit. All right, let's find the error then, the remainder of this first degree polynomial. If we were to plug in 2.5, must be less than or equal to m over 1 plus 1 factorial. And then we have 2.5 minus 2 to the 1 plus 1 power. M, remember, has to be, or should be, greater than the next derivative at some value z. So from that information they gave us, we know that 3 is greater than the next derivative. So m will be 3. Okay, if we simplify this a little bit more then, we have 3 over 2 factorial. 2.5 minus 2, 1/2. 1/2 squared is 1/4. So what we can say then is the amount of error is going to be less than, hold on, let me catch up to myself, is going to be less than 3/8. The difference in the answers, if they ask you for the error bound, we would add and subtract that from the value we found. When we're estimating the error, we just stop when we find r. Okay, let's look at one last example. Use a third order Taylor polynomial for the natural log of x centered at 1 to estimate the natural log of 1.5, and then estimate the amount of error. So not the bounds, but what is the error? What is r? Go try. This is not one that we have done yet. We've not written a polynomial for the natural log of x. So let's go see if you can do this from scratch. Okay, welcome back. In order to write the polynomial for this, we need to find all of the derivatives. So first of all, oops, I'm still in highlighter mode. F of x is the natural log of x, and we're centering this at 1, so we need to find f of 1. The natural log of 1 is 0. Okay, then we're going to find the first derivative. First derivative is 1 over x. F prime of 1 is 1. Second derivative is negative 1 over x squared. Plugging 1 into that is negative 1. And we're looking for the third order, so the third derivative then is 2 over x cubed. And plugging 1 into that gives us 2. Okay, using that information, now I'm going to write the polynomial. F of x is approximately this third order polynomial, which is f of a, so 1, plus, oops, f of a was 0. I was looking at the wrong one. F of a is 0 plus f prime of a, so that's 1 over 1 factorial times x minus a to the first, plus negative 1 over 2 factorial times x minus 1 squared, plus 2 over 3 factorial times x minus 1 cubed. Simplifying this, we get x minus 1 minus 1/2 times x minus 1 squared, plus 3 factorial is 6, 6 is 1/3, x minus 1 to the third. Okay, this is a polynomial that will approximate the natural log of x. Now what we're looking for is the natural log of 1.5, so I'll replace x with 1.5. Oops. And if you don't mind, I'm going to skip some steps. So for example, I had 1.5 minus 1, so I'm just going to write 1/2. And then 1.5 minus 1 here, so that's 1/2 squared. And this is 1/2 cubed. Okay, I'm going to simplify because this is going to be more readable, I suppose. 1/2 squared, 1/4 times 1/2 is 1/8. And then 1/2 cubed is 1/8, so that's 1/24. Common denominator gives me 12/24 minus 3/24 plus 1/24. 12 minus 3 is 9, plus 1 is 10, so this is 5/12. The natural log of 1.5 is approximately 5/12. Okay, so that's the estimate. Now we're going to figure out how far off are we from the actual, or what's our bounds anyway. So we're going to find the remainder for this third order polynomial for 1.5. We know that it will be less than some value m over 3 plus 1 factorial times 1.5 minus 1 to the 3.1, or 3 plus 1. Okay, simplify this a little bit before I find m. M over 4 factorial, so this is m over 24. 1.5 minus 1 is 1/2. 1/2 to the fourth is 1/16. We've seen this number before. So this will be m over 384. Okay, now comes the fun part. This is a new way to find m. So we need to find the next derivative, so we need to find the fourth derivative. As a refresher, the third derivative was 2 over x cubed. So the third derivative was 2 over x cubed. So that means the fourth derivative, that's going to help us find m, is negative 6 over x to the fourth. All right, so what I'm going to do, I'm going to graph this just to kind of get a visual of what this might look like. Negative 6 over x to the fourth looks like this. And I'm trying to find a value m that is as large as possible. So if I look at the fact that we are on this exponential, so I'm talking about magnitude of m, remember, because m was either negative or positive, I can see that at 1, because that's where we're centered, at 1, the value of the function is negative 6. And at 1.5, the value is not as big in its magnitude. So what I'm going to do then is I'm going to use this value 6 because I know that 6 is larger than the second derivative, or the next derivative on this interval. That is as large as it'll go on that interval, is negative 6. So I'm going to use 6 for m because we're talking about absolute value here. So the absolute value, we've got 1.5 and we've got 6 over 384, which probably reduces, but that's okay where we're at. So the question said, did it find just estimate the amount of error? Let me just reiterate, because we're looking from the interval from 1 to 1.5. 1.5 is actually what we're calculating, And I know that when I plug 1 into this function, that is as low as it's going to go on that interval from 1 to 1.5. So that means -6 is the smallest value. And since we're looking at absolute value, I know that 6 is as large as I'm going to get because the values just decrease from there.